Hello. Today we're going to learn 10.2 calculus with parametric curves. In this section, we're going to find the tangent of the parametric curve and the area enclosed by the curve, and also the arc length. Okay, so let's start from the first one, which is tangent. So tangent in calculus 1, we know that's the derivative of the function, right? So for the parametric curve was the tangent. The first we're going to find tangent. So we're going to do this way. Firstly, we need to know our parametric curve should be x equals, we can say xt, y equals yt. Okay. So if dx dt is not 0, so you can see here we have two functions, right? Two functions. Now let's see, dy dx. dy dx is still the slope of tangent, just means derivative of the function, right? Just means the function is given by another way, but still a function. So let's see, dy dx equals, we are going to do this way, dy over dt times dt over dx. You can see if we cancel the dt, they are the same thing, right? And now we are going to put dx dt in the denominator, okay? Like change dt dx times dt dx into dy by reciprocal of dt dx, that is dx dt. So the other way, we can also write down this as y prime t over x prime t. Okay, so the first, this is Leibniz notation, this is Newton's notation. It's like before we have f prime x, and the other way is dy dx, right? So just a different notation. So let's see, then what is the first formula? Dy dx, which is just dy dt over dx dt. That's the first derivative. Now let's take a look at the second derivative. The second derivative is going to be this one. And this equals what? Dy dx. First derivative, right? So right now we change this into, okay, same thing, dy over dx. This is a function in terms of t. Okay, so this is also like a part, same as this first formula. So it's going to be dy dt dt, okay, over another dx dt. So if we write this in a better way, it's going to be second derivative of dy dt, okay, over dx dt. That's the second derivative. Now let's take a look at the example. How to find the tangent to the curve. And the curve is given by this: x equals secant t, y equals tangent t, and the t is from negative power 2 to power 2. So we want to find this curve at point root 2, 1, and where t equals power 4. Okay, now let's take a look at this problem. So the curve is given by parametric equations. So by using the definition, we know the slope. Okay, let's find the derivative. Slope is the derivative, and derivative of parametric equations given by the formula, the first formula, so which is dy dt over dx dt. And the dy dt means tangent t derivative. Tangent derivative should be secant square, right? And the dx dt is secant derivative, which is tangent secant t. And now we simplify, we can cancel one secant. So this is secant t over tangent t. And we can further simplify this because this secant t is 1 over cosine and tangent is sine over cosine. And we can cancel those two. So it's 1 over sine t. You can still keep a secant t, but you know, when we evaluate slope at the t equals power 4, you still need to calculate secant power 4. So secant power 4, you still need to change that into 1 or cosine. So why not? We simplify right now and then plug in t directly. So what's the slope? Slope is dy dx derivative when t is pi over 4. Now we just plug in t equals power 4 into our derivative. So sine power 4. Sine power 4 is root 2 over 2. And to simplify this is 2 over root 2. And the 2 actually is root 2 times root 2 over root 2. So it's going to be just square root of 2. So that is the slope of the tangent. And we want to find the tangent line. Same thing, we use the point slope equation. Okay, the point is already given. So the point, if the point is not given, we need to know how to calculate the point by ourselves. We just plug in this t into our x and y. We can find the point, right? X and y. So let's see how to find write down the tangent line. So y minus 1 equals slope x minus root 2. Okay, that is the tangent line. X is 2 cosine t. Y equals 2 sine t. T equals power 4. Okay, we want to find slope when t equals power 4. I'm going to give you the solution later. That's problem. And you can see we do the same way, find the derivative, and then plug in t equals power 2, power 4, and then we find the slope. After we find the slope, we try to use the point slope equation, but for this problem, the point is not given. So we just need to find the point by ourselves. So how to find the point? We plug in power 4, and into x and y, we find the point root 2, and then just write down the point slope equation. Okay, that's the exercise problem. Now let's take a look at example 2. We're going to find the second derivative. Okay, we're going to find d squared y dx squared as a function of t if the parametric equations are given by x equals t minus t squared, y equals t minus t cubed. Okay. So the second derivative we know is the derivative of the first derivative. So definitely let's find the first derivative. Okay. First derivative, same thing as before. That's going to be dy dt over dx dt. Derivative of y in terms of t should be 1 minus 3t squared. Here should be 1 minus 2t dx dt, right? That's the first derivative. Now we are going to do this to another, like a treat this as y. Okay, our new y and the dx. So use the formula, so which is going to be just derivative of that one, the top function, over dx, another dx dt, right? Dx dt. 1 minus 2t. So the final answer for this one should be, okay, we can use quotient rule for the numerator. It's going to be 1 minus 2t squared in the numerator, but combined with another 1 minus 2t, so going to be 1 minus 2t cubed. And the numerator going to be f prime g minus fg prime. Quotient rule, right? quotient rule. So it's going to be negative 6t minus, okay, say plus 2 times 1 minus 3 t squared. If we don't simplify, that's the final answer. Okay. Second derivative. Now we can try the exercise problem. We can do 2 problems here. I'll just do 1. Okay. Same thing, x and y are given by the parametric equations. So the first derivative, dy dx. Okay, so here I give you the solution directly. dy dx, dy dt, dx dt. That's the first derivative. So take another derivative. Okay, let's do parametric curve equation. So for parametric equation, the derivative should be dy dt over dx dt. So over another dx dt and derivative of this one. So final answer should be 2t cubed 6t times 2t minus 3t squared minus fg prime. Okay, f prime g minus fg prime. That's the final answer. That's the first thing we need to know is the tangent. That means the first derivative. And the next we're going to do area, okay, of the curve if the curve is given by ft/gt. Okay. So how to find the area under the function? In calculus 1, we learned the area can be calculated by definite integral. So definite integral is a to b and function and then dx, right? So right now we just want to replace the y by gt, okay, and the dx, if you look at our x equals ft, so dx is like the differential we learned before, so which is f prime t dt. Okay, so differential, right? So f prime t dt. So our formula for parametric curve should be, and right now t is the variable, so the boundaries, lower limit and upper limits, they are not a to b, they are the value boundaries for t. So we can say alpha to beta, and here gt and f prime t dt. Actually, you don't need to memorize this formula. We can always change y into g, ft, dx into f prime t dt. That's the formula for the area. So we can take a look at example 3. Find the area under one arc of the cycloid, and is given by x equals r theta minus sine theta, y equals r 1 minus cosine theta. Okay. So here r is the constant, variable is theta. Theta is the variable. We treat r as constant. Now let's take a look. By using the formula, okay, so here we shouldn't have one arc of the cycloid. So the graph of the cycloid is given by this. Okay, and then one arc, so theta from 0 to 2 pi. Okay, this is given. Theta from 0 to 2 pi. Let's see. area equals, first set up the integral 0 to 2 pi, and the y, which is r, 1 minus cosine theta, right? And the dx means we take the derivative of x. So going to be constant is r, 1 minus cosine theta, and d theta. Simplify this, becomes 0 to 2 pi, r squared, 1 minus cosine theta squared d theta. R is constant. We can take the constant in the front to the front, 1 minus cosine theta squared d theta. Because we just, theta is the variable, we do the integral respect to theta. And simplify, expand the square thing, 1 minus 2 cosine theta plus cosine square theta d theta. And here for cosine square theta, in calculus 2, we learned how to evaluate this integral. So in order to evaluate this integral, we use the double angle formula to decrease the power. So we change cosine square into 1 plus cosine 2 theta over 2. So let's see. Right now, we can just copy everything here and have 1 plus cosine 2 theta d theta. Now we can evaluate the integral. So integral 1 should be theta, and the integral cosine theta should be sine theta. And so here 1/2 theta. Okay. And the cosine integral should be sine 2 theta. Okay, cosine 2 theta. So should be sine 2 theta over 2. Right? So here, and divide by another 2, so should be sine 2 theta over 4. And whole thing theta from 0 to 2 pi. Because this is definite integral, we need to plug in the upper lower limits. Now let's take a look at the sine. Sine 0 and sine 2 pi, they both are 0. So if we look at the sine term, because the lower limit, upper limits, they are both just like 0 to pi. So you can just make them into 0. That's easy. Okay. So this is going to be r squared, and the theta and that one we combine. So going to be 3 theta over 2 and 0 to 2 pi. And when we evaluate this thing, so r squared, so 3 times 2 pi, simplify, so it should be 3 r squared pi is the final answer. Okay, the area of the curve, under the curve. Now let's take a look at this exercise. We just try to do more, practice problems. So the first one we can do t equals x equals t squared, y equals t to the 6th. This is a pretty easy one. Can give you the answer here. So area equals 0 to 1, y dx is just like a 2t dt. Oh, that's y is t to the 6th, right? Now just simplify. So take the 2 to the front, t to the 7 dt, and evaluate this one. So t to the 8 over 8, 0 to 1, right? So pretty easy. So the final answer should be 1 first. Okay, 1 first. Second one, a cosine t, b sine t, t from 0 to 2 pi. Give you the solution here. Same thing, area equals 0 to 2 pi, b, this is y, and take the derivative of x, negative a sine t dt. Take the negative ab to the front, because they are constant, 0 to 2 pi, sine square t dt, and for the sine square, we're going to do the same thing. Decrease the power, use double angle formula. So sine squared t should be 1 minus cosine 2t dt. Okay, and now evaluate the integral. You can take the 1/2 to the front. So it's going to be t minus sine 2t over 2 and t from 0 to 2 pi. So sine, because you evaluated them at 0 and 2 pi, so you can treat this term as 0. So it's going to be negative AB over 2 times 2 pi. So cancel the 2, so negative AB times pi. That's the final answer. Okay. So that is all about the area.